Okay, so we're going to go through the how to manually create an NWB file that contains extracellular electrophysiology data. So this includes an electrode table, which describes metadata about what electrode you recorded from, acquired raw voltage data, local field potential data, so potentially processed version of the raw data, and spiking data from spike sorted units. All right, so we have some imports. This is largely going to build upon the tutorial that Ryan just gave. I guess if you're watching this on YouTube, check out this tutorial first. The one thing we're going to copy over is just the creation of the NWB file, because we actually just need that NWB file object. You'll likely also need things like trials table, which you can learn about in the previous tutorial. But we're just going to jump right into extracellular electrophysiology. So the first thing we want to do is create an electrodes table, which is going to allow us then eventually to store information, store the data that's recorded from those electrodes. So I have here a diagram of an electrodes table, which is a dynamic table. So it inherits from that. And it has a number of additional columns, many of which are now optional. But one of the ones that's not optional is an electrode group, which then references a device. So in order to create this electrode table, we first need to create a device, and then we can create an electrode group, and then we can reference that group in the electrode table. So a device here corresponds to like a probe. And electrode group is most often used if you have like a multi-shank probe. So if you have groups of electrodes, that is actually kind of not as common now as it was when a few years ago. So if you have a probe where the electrodes aren't grouped into natural groupings, you can just have a single group for a probe. Okay, so the first thing we want to do is create a device. So NWB file has this method, create device. I'm going to give it a name, a description, and a manufacturer. So that creates the device and links it into the NWB file. And now we want to create an electrodes table. So I'm just going to say, okay, let's say we have a multi-shank probe where we have 4 shanks and 3 channels per shank. So, and I also want in the electrodes table, because it's a dynamic table, and this is true of all dynamic tables, you can add custom columns. So in the trials table example from the basics tutorial, you saw adding the correct column to that table. So we're going to do something similar here and add a label column to this electrodes table just to show you how to add custom metadata to the electrodes table. So that you add that column by calling NWB file.add electrode column, give it a name and a description. And then I'm just going to iterate through, and I have a little script here that generates the electrodes table given 4 shanks and 3 electrodes per shank. So first I'm just going to iterate over the shanks, and then for each shank I'm going to create a corresponding electrode group by calling NWB file.create electrode group with a name, a description, the device, which we have previously created up here, and location. Now here, the electrode group is creating essentially a soft link to this device. So the device isn't stored within the electrode group, and you can reference the same device from multiple electrode groups, which is also what we're doing here. So this isn't copying that device information. And then for each of these shanks, we're going to have a for loop per electrode, and then we'll just say add electrode. And so we're going to add the electrode group, which is again a reference or like a soft link to the electrode group object that we created right here. Label, which is our custom column, and location, which is a required column. And then this iterator just helps us iterate through all of these electrodes. Now you can visualize this table with well, first of all, it's now present in NWB file.electrodes, and if you want to view it as a pandas data frame, you can call to data frame. So let me just quickly show you what that looks like on the MATLAB side. So again, we create an NWB file. Same diagram here. Again, we have this kind of double nested for loop that's first by shank and then by electrode. So here we have a little bit of a different syntax for creating the dynamic table object. So what I'm going to do here is create an internal table object. It's kind of a newer type of object that is in core MATLAB and newer versions of MATLAB. And we have the ability to convert from this table object to an NWB dynamic table. So, so first, I'm going to give it the column names, location, group, and label, and then create a table object from those column names. And then, just like before, create a device with a description and manufacturer. One of the differences between PyNWB and MatNWB is that with PyNWB, you'll notice that the name is defined as we create the device. So there's a name here. With MatNWB, the name is defined as we add it to the NWB file object. So we have this device, and then we set it, nwb.general_devices set, okay, here's where we put the name, and then the object that we just created. And then we have this double nested for loop, first looping over shanks. We create the electrode group object, very similar to the Python side. One of the big differences, though, is here. So on Python, you just said device equals device. And it knows internally to create a soft link to device through the logic of that class. That's not true of MatNWB, so you have to say, set this device to a soft link of the device object. So it's just actually a little bit more explicit here on the MATLAB side, where you're saying you're not going to put necessarily that device object inside of the electrode group. You're going to reference it as a link. Okay, and then we're going to add this electrode group by calling nwb.general_extracellular_ephys.set, and then that takes the name and then the object. And then this is another thing that's a bit more complicated on the MATLAB side. It's an object view. So this is another type of reference when you want your reference to be put into an array. So this is like an array of references. So now we're going to iterate through the electrodes, and we'll generate a label for each electrode, and then take this table and we'll just concatenate onto the table unknown for location, group object view, which is kind of a link to the electrode group under the group column, and then electrode label under the label column. So what we end up with is this table. So that's one of the nice features about building this up as a MATLAB table and then converting it after the fact to a dynamic table, is you get this really nice rendering, and you can use, it's kind of similar to a pandas data frame in MATLAB. So you've got location, group, label as columns of your table, and then you can call this utility function table to NWB, and it creates an electrode table. You just need to add a description, and once you have that object, you can add it to the appropriate place within the NWB file, which is nwb.general_extracellular_ephys_electrodes. I would probably recommend copying and pasting or building off of this tutorial as opposed to writing all of this yourself. So this next section is just an explanation of how we're using links here, where we have electrode group and we're using object view to basically create this this array of references. So each of the elements of this array points to a specific electrode group object. Okay. So now we have our electrodes table. And now we can actually add the recorded data that we probably started out with wanting to add. So I'm going to introduce the electrical series object, which is a subtype of time series. So it inherits all the properties of time series and adds more. This would be an appropriate type to use for raw voltage traces as well as local field potential data. And as the diagram down here shows, it inherits from time series and adds, well, first of all, it constrains that the units are in volts, and it adds electrodes, which is a dynamic table region. So a dynamic table region is a way of linking to specific rows of a dynamic table. So here we've already created our electrodes table, and we'll use this dynamic table region to reference rows of that table. In this case, we're just going to reference all of the rows, but it's possible to create an electrodes table that has many electrodes, and then subset are being recorded with specific electrical series. If you're only recording from a subset at one point and then a subset from another point, or maybe you have different sampling rates for different electrodes, you can use that kind of flexibility to create multiple electrical series that might be recording data at the same time or at different times. Okay, so what we need then is this dynamic table region, and we create that by calling NWB file.create electrode table region. And all we need to do is pass what electrodes we want to reference. So this is just referencing all of them, a list range that goes from 0 to electrode counter, and a description of this dynamic table region. So this provides the link between the electrical series, which has the data, to the electrodes table, which has metadata about the electrodes that recorded that data. Okay, so now that we have this electrical series that points to the electrodes table, we can create our actual electrical series. So let's just generate some raw data and call electrical series. We'll give it a name. You can name it anything. If you only have one and there's no need to specify, you can just call it electrical series. Pass the data, pass this dynamic table region. Here, again, you can use starting time and rate. Here I'm saying the starting time is 0 and the rate is 20 kilohertz. You can also specify time with timestamps. For electrical series, we often see rate and starting time because it usually has a constant sampling rate. But if it doesn't, you have the flexibility to use timestamps here. And then since this is raw data, I mean, it's simulated, but we'll say it's raw data. I added it to acquisition here, so NWB file.add acquisition raw electrical series. So just to flip back to the MATLAB side to show you what that looks like. Okay, so first we need to create that dynamic table region. And it's slightly more complicated here on the MATLAB side, so we actually call the dynamic table region class, and then we use object view to reference the electrodes table. And the description is all electrodes, and then for the data, we're going to just go 0 through the height -1. So this is actually something I wanted to mention. Indexing in MATLAB is 0 indexing. So when we're specifying what rows of the table, that's done with 0 indexing. Might be a little bit foreign to MATLAB programmers that are used to 1 indexing. So the data starts at 1. In Python, it starts at 0, and we've chosen 0 indexing. So if you want to set up indexing, you have to use 0 indexing here. Okay. Once we add that electrode table region, you can create your electrical series. So types.core.electrical series. Here again, starting time and rate. We're going to generate some raw data. Use this electrode table region that we just created and specify that the data is in volts. Once we have that object, we can set it using nwb.acquisition.set. Name it anything you want here, but we'll just use electrical series as the default and set that to this electrical series object you just created. Any questions so far? Yeah. Yeah. No. Generally, that would be an n by 16 array inside of one electrical series, unless you had a really good reason to split it up. So then, yeah, I mean, technically you could create 16 different electrical series and then have each one reference a different row, but that's not what I would recommend, particularly if you're planning on doing some kind of spike sorting on it, that it's going to use multiple channels simultaneously. You're going to want those to be fed into the spike sorting algorithm all at once, so it's better to store them all in one block. Plus, it will probably compress better if you store them all in one array. Yeah. So that's true. So if you had, there might be good reasons to split up into multiple electrical series. Like if you had different types of recording devices, maybe they have different sampling rates or something. If you have different sampling rates, you basically have to. But yeah, there might be a reason to create multiple ones. But if they're all kind of part of the same probe, you probably are going to stay in one. Yeah, different conversion factors would be another reason. Yeah. Though we have some flexibility with conversion factor. Yeah, we do allow for channel-wise conversion factors if that is needed. So it's not, if that's your only reason, then we can work around that. Okay. LFP data. So let's say you've done a little bit of processing, maybe some bandpass filtering for some frequency ranges of interest, and you have processed data that we're going to call LFP. I'm going to generate some here. It's exactly the same as before. So it's just LFP data because I've generated a different data set, but I'm linking to the exact same electrodes table to say it's recorded from all electrodes. And then, okay, so similarly to how we put the spatial series in a position object to indicate that it's the position of the animal, similarly to that, you can put an electrical series inside an LFP object to indicate that it's representing LFP. So here's the LFP object, and you can assign it like this. So now we have this LFP that contains an electrical series. You can also use filtered ephys here as an alternative to LFP. And then, yeah, so now we just need to create a processing module. So NWB file.create processing module. We're going to name it EC-ephys. Again, we would like to default to the names of the modules within NWB. So if you have extracellular electrophysiology, you can name a processing module anything, but this is kind of a best practice default. And then once we have that module, we can add LFP. And we're adding it to a processing module because it's not raw data, it's processed, there's some kind of offline processing filtering of this data that we might want to change. Okay, now spike times. So spike times are stored in an object called units, and units is a subtype of dynamic table. So just like the trials table and just like the electrodes table, as a dynamic table, you can add optional columns to this. So that allows you to add metadata, flexibly add metadata that correspond to units. The only required field here is spike times. I think that's a required field of the units table. But we're going to add quality. So we're going to say, okay, we have some quality metric that we use internally, and we want to add this to the table. All right, so I'm just going to generate some spike times here. So I'll say a random firing rate is 20 hertz, number of units with 1 kilohertz resolution, and for 20 seconds. And so here's just a quick snippet of code to actually generate spike times, randomly generate those spike times. And then once we have the spike times, so this is just a list of times, we can add that here. So NWB file.add unit, spike times equals spike times, and then quality, I'm just going to say all of them are good, though of course you can change that value. Now notice here, spike times is a list. So we can store lists as cells of a table, which is what we're doing here. And then once you have that table, you can call toDataFrame to get a printout of it, and this will just convert it to Panda's data frame, and you can analyze it however you want as a data frame. Okay, so showing that on the MATLAB side. Again, the LFP stuff is very similar. Electrical series, you create that with the dynamic table region. You can then create an LFP object and include the electrical series with the name electrical series in it. Create an EC-EFIS processing module and add LFP to that processing module, and then add that processing module to the NWB file. Here again, we're just generating some random spike times, so number of cells firing rate. We have some general data here. This is a cell array, and each cell has a number of spike times in it. It's not the same number. So because this is not the same number, it's a type of data that we call a ragged array. It looks like this essentially, right? So like you can't simply store spike times as a rectangular array, as a normal array, because there are a different number of spike times per unit. So what you can do, and what I've seen sometimes, is just like NaN padding this, and that's one option. But instead of doing that, we have a different solution where we basically have a structure that represents dynamic array, ragged arrays within dynamic tables. So how this works is you basically take all of your spiking data from all of your units and you just stack them up in a single array. So this is the spike times of unit 0, 1, 2 are then all stacked up in the same array. This is from 0, this is from 1, this is from 2. And that's in your spike times array. And then there you have a second array which just indexes into this. So it says that that 0 through 6 is from unit 0, and then 6 through 9 is from unit 1, and 9 through 11 is from unit 2. So between these two arrays, you can represent essentially one array that is ragged, that has a different number of cells per row. So all of this is kind of extracted away from the PyNWB API. PyNWB API is doing the same thing. You're inputting this array, and it's forming on the back end, it's forming these two arrays. One is keeping track of the index, and the other one is storing all the data. We don't have those same convenience functions on the MATLAB side, so you kind of have to know a little bit more about what's happening under the hood. This is essentially what's happening. So we have this utility function where you can input the spikes, and it will give you this spike times vector and this spike times index. Just know that's what this is mapping to, right? This spike times index maps to this, and this spike times vector maps to this. It contains all the data. So when we create our units table, so the last time I created a dynamic table, I showed you first the creation of a MATLAB table object and then converting that to a dynamic table. This time we're doing it a different way just to show you other options. So this is just directly creating it from the constructor of the units table. So you have to specify your column names. Here we have spike times, the description of the table. You specify ID, which is the rows of the table, which generally are just integers, int64s going from 0 to the length -1, again, because this is 0 indexed. Spike times contains all of your spiking data, and spike times index contains the indices into that large vector that says how it maps to the individual units. We're close to the end, so I'm just going to plow through before asking for questions, unless there's anything pressing. Okay. This section goes through less used neurodata types, so event detection, spike event series. These are generally types that you would use kind of in the middle of a processing pipeline. So they're not raw data, and they're not the end. They're like kind of intermediate, and you can put them in. We don't see them often used because these days, people change the way they process data, and they might not be a good way of representing the data that you want to represent. So generally, people just store the raw data and the result of processing. So you were able to use some of these types to do intermediate things. I'm just going to skip over that for now, and I'm happy to talk to anyone who wants to store that data. So writing it is as simple as with NWB HDF5IO, that you read that as NWB HDF5IO, by the way. Open up a file in write mode as IO, and then IO.write NWB file. In MATLAB, it's actually easier on the MATLAB side for once. NWB export this object, and then you just say the path of the file you want to save it to. Okay, and then a bit about reading. So the reading is going to be pretty similar to what Ryan showed you, but just to kind of show you in the context of extracellular electrophysiology. You call NWB HDF5IO on that file in read mode. You say io.read, and then here's how you access some of the data types that we just wrote in this tutorial. And if you want to access all of the data, for instance, for LFP electrical series, you call .data, and then this colon operator loads all of it. That is often not what you want to do. So if you want to load just a region of it, you can call .data, and then this gives you the first 10 rows and the first 3 columns. And then also here's how you would read spike times for a specific unit. So read NWB file.units, the spike times column, and then 0. This will give you all of the spike times for the 0th unit. On the MATLAB side, you have, you read it like this. So I'm just going to assign this to NWB2. So NWB2.processing.get ECEFIS, and then within that LFP, and within that electrical series, .data, and then if you want to load that data all at once, you can do load. And again, here you just use standard MATLAB indexing syntax. And so this will actually not read all of data into memory. It will only read this region into memory. So if you have a really big data file and you call it like this, you'll only be reading this little chunk. And then if you want to pull out spike times, nwb.units.get the first row, and then spike times is a cell array, so you can index that like you normally would in MATLAB. So in this case, you've gone back to MATLAB indexing because you're indexing a normal cell array in MATLAB. So you would say 1, and that would give you the first unit. Okay, so that is extracellular electrophysiology. Again, just like the other tutorial, you can download the source code. You can download it as a Jupyter notebook and run it yourself. And there is a kind of equivalent type of file on the MATLAB side that you can access. Let me see here, tutorials. Yeah, so it's ecefis.mlx. That's their kind of version of a Jupyter notebook. So you can load it up that way if you want to run the MATLAB side. Okay, any questions? Yeah, Vincent.
Yes, maybe at several steps during your presentation, this for web is space.
Yeah.
For loading the metadata code.
Yeah.
Some metadata early on, and for the community of Sony, this kind of thing.
Yeah.
Manually, so how well?
Yeah. Really well. Let me pull it up. You are kind of stealing my thunder for tomorrow, but that's okay. So here we have downloaded some data on Dandy, And then ingesting that into Spike interface is spike extractor dot read NWB recording and then read NWB sorting. And that will load the data and metadata as much as we have supported. And this is actually directing it to the same NWB file because this one NWB file contains raw data as well as the results of spike sorting. So you should be able to then do all of your spike sorting from the recording object and do some visualization of the sorting from the sorting object.
And for the probe,
So the probe, so we ingest the XY positions of the electrodes. I guess the one thing that we don't support yet from probe interface is the geometry of the probe itself. It doesn't tend to be used that often in spike sorters as far as I know. So that's really more just about supporting visualization of that data, which we don't really have that yet. But the geometry as far as the XY positions get imported automatically. Mm-hmm. Maybe internally. I haven't seen much of that published to Dandy yet. I think mostly, to be honest, people are probably using just ad hoc formats for most of that data, though be happy to support writing of those intermediate results if that's useful.
With NeuroConv and Spike interface, do you think that covers most of what is here?
Yeah. So yeah, I guess I should have prefaced all of this with you should see if NeuroConv covers your format before you go down this road. So maybe I'll edit our YouTube video to put this first. So you can go to Conversion Gallery and then under the extracellular electrophysiology, take a look at these formats, see if they work for you. So if you, for instance, have Neuralinks data, here's how you install it, and here's how you run it. And this will give you for free the electrodes table and will give you the electrical series. And on top of that, it will apply data engineering, chunking, and compression, which you'll learn about tomorrow, and will also read the data piecewise. So often your data sets are so big that you can't load them all into RAM. So we'll cover details of that, how to do that yourself, but all of that's done for you for free with NeuroConv. Yeah. Yeah, it depends. So, I mean, for instance, with Neuralinks, you'll find sometimes that the files are separated by channel. So that's just not indicating really anything about the recording. That's just a decision they made with the data format, right? So in that case, we concatenate all of them into a single electrical series. However, if you have multiple files because you've stopped and started your recording, it may make more sense to create multiple electrical series objects. And that might be somewhere where we don't 100% support that use case yet. It's worth trying and letting us know if there are issues with it. That's getting kind of maybe into a more advanced use case depending on the details. Yeah, Thomas. Yeah. Yeah, so So I was saying most of the time in electrical series that it's a constant sampling rate. But yeah, if there are hiccups in the system, I mean, especially if you're going for weeks at a time, that can happen. And then you might just store timestamps. You might just go with, even if it's a week long. You know, it's really a judgment call, right? Like if you're truly not recording for 5 minutes, maybe it would be better to have 2 electrical series. I don't know. At a certain point, it's going to come down to the details of your experiment and of the analyses you want to do. But those are your options, to use timestamps to express the irregularity or to create multiple electrical series. Well, you're going to, of course, have to store that data. You can throw compression at it, which tends to help a lot. But yeah, it's more data. It's usually very small in comparison to the actual data, but it is potentially adding more data. Yeah.